Hello, I'm covering section 4.4 about evaluating logarithms and the change of base theorem. So we have learned so far that the logarithm with base a of x equals y if and only if a raised to the y power is equal to x. So a is known as the base, and the most important bases are 10 and e. So those are the ones you can evaluate immediately with the calculator. We're going to start with the common or the decimal logarithm. Okay, so the common or decimal logarithm is nothing but the logarithm with base 10. So if you look at the calculator, you have two buttons, which are log and ln. And this is denoted as log of x. So log of x, if you see the empty base, it is understood that is logarithm with base 10. And let me show you, I'm sure you have a scientific calculator, you are going to have it. But I'm just going to share the one in the computer, and you can see these buttons, log and ln. So if you see the button log, that's logarithm with base 10. What we know for sure is that logarithm with base 10 is 1. So again, if you don't see the base written, it's logarithm with base 10. So on a calculator, you have the button log. So that's the button you're going to see on a calculator. And you can quickly evaluate logarithms with base 10, like logarithm with base 100,000. Well, you know this, you can do this with the definition, this logarithm with base, or logarithm of 10 to the 4th, and that is 4. So let's compare to what the calculator says. So logarithm of 10,000 is 4, as expected. Also, logarithm with base 244. Well, for that one, I don't have the definition. I mean, I cannot do that. I don't know how to do that without a calculator. I would be looking for a power of 10 such that 10 to that power is 244. But in a calculator, it's just one button. So that is logarithm of 244, and that's approximately 2.38740. We'll round up. That's approximately 2.3874. So 10 raised to that power is going to be 244. Or logarithm with base 0.173. Okay, so calculator. I'm looking for the logarithm of 0.7. Okay, so logarithm of 0.173. The decimal logarithm, and that's going to be a negative number. So that's going to be approximately negative 7620. Okay, so far. Okay, so I'm going to show you an application. So applications, and models with common logarithms. Okay, so I'm going to show you the pH. So that's one application. So in chemistry, the pH of a solution is defined as the opposite of the logarithm of H3O plus, where that value is the hydronium ion concentration in moles per liter. So I'm not going over the technical stuff. The pH value is a measure of the acidity or the alkalinity of a solution. If it's 7, it's going to be neutral. The closer it is to 14 is alkaline, and the closer it is to 1, the solution is acidic. So pure water has a pH 0, now 7. Substances with pH values greater than 7 are alkaline, and substances with pH less than 7 are acidic. Okay, so I'm going to copy this formula, and I'm going to go over example 1. Okay, so yeah, let's share the board. That's on page 450. And we're going to use this formula to answer or to go over example 2. Okay, so let's find the pH of a solution with H3O plus equals 2.5 times 10 to the negative 4. Let's plug it into the formula. pH, it's the opposite of a logarithm of 2.5 times 10 to the negative 4. Okay, let's evaluate it on the calculator. So this is 2.5 times 10. So I did something wrong. So that's 2.5 times 10 raised to the negative 4. We're going to find the logarithm of that. Take the opposite value. So that's going to be 3.6. It's going to be acidic. So that solution is going to be acidic. That's approximately 3.6. Okay. The other thing you could have done is use the properties. So I already did like that. I did directly. But if you want, you can use the properties. This is the opposite of log of 2.5 plus log of 10 to the negative 4. So this is the opposite of logarithm of 2.5. And then log of 10 to the negative 4. This becomes negative 4. And the opposite of that is going to be 4, which is indeed approximately 3.6. Not surprisingly. And B, find the hydronium ion concentration of a solution with pH 7.1. So now this is the opposite. So part B. This is the opposite of logarithm of 2.5, not 2.5, of the H3O plus whenever this is 7.1. So we need to find the value of H3O plus. Okay. So logarithm, this means that logarithm of H3O plus is equal to negative 7.1. But logarithm is a logarithm with base 10. This means that h3o plus is 10 raised to the negative 7.1 using the definition of logarithm. And that's going to be approximately, so that's going to be a number in scientific notation. Let's put this on a calculator. This is 10 raised to the opposite of 7.1. And in scientific notation, this is about 7.9 times 10 to the negative 8. So that's the hydronium ion concentration. So this is one application, the pH of a solution, and another application is decibel rating. That is the intensity of sound. So there's a possibility that you have heard that that term. And yeah, we did that. Okay, well, I'm just going to copy this problem. The loudness of sounds is measured in decibels. We first assign an intensity of I0 to a very faint threshold sound. That is the minimal sound that a healthy human can hear. That's the threshold sound. If a particular sound has intensity I, then the decibel rating of this louder sound is given by a formula involving the common logarithm. Question: find the decibel rating of a sound with intensity 10,000 times the threshold of sound. Okay, so I know what is I. I is 10,000 times the threshold sound. So the decibel rating, we plug this into the formula, that's 10 times logarithm of 10,000 I0 divided by I0. So that's a constant. These two can cancel out. And it's 10,000 log, or 10 times log of 10,000. And 10,000 is 10 to the 4th. So this is 10 times logarithm of 10 to the 4th, or 10 times 4. So the decibel rating is 40. So that's 10 times, this is 4. So that's 10 times 4, or 40. So the decibel rating of that sound is 40. Or the intensity of that sound is 40 decibels. So the sound has a decibel rating of 40. Okay. So what we did was the decimal logarithm. The calculator has two buttons, log and ln. So we did the logarithm of x. When the base is not written, it is understood that the base is 10. So this is equivalent to 10 to the y equals x. Y is the number such that 10 raised to that power is equal to x. And the other important base is base e, the number e. So the natural logarithm is the logarithm with base e. And I'm copying that. For all positive numbers x, the natural logarithm of x is the logarithm with base e. But logarithm with base e that's usually never written. By definition, y equal the logarithm of x is equivalent to e to the y equal to x. On the calculator, you're going to see the button ln. So by the inverse properties, the natural logarithm of phi raised to the third power is going to be 3. The natural logarithm of 287 is going to be what? It's going to be, we have this button ln, so that's going to be natural logarithm of 287. That's approximately 5.497. So 287, that's 5.659 approximately, or 6595. So e, the number e raised to that power is going to be 287. Also, the natural logarithm of 0.0135. Let's check that. This is 0.0135. The natural logarithm of that's approximately negative 4.3051 approximately. So that's 4.3051. That's negative. Yeah, that was a negative number. So e raised to that number is going to be approximately, it's going to be 0.0135. And the natural logarithm of 1 over e to the fifth power, e to the fifth power is e to the negative 5. Just using the inverse property. Okay, so we're going to see an application. An application of the natural logarithmic function. I'm trying to find this. Okay, so that's number 70. So we have this long, this very long graph, or this very long problem. The bar graph on the right shows numbers of leisure trips within the United States in millions of person trips of 50 or more miles one way over the years from 2009 to 2014. So that's function involving natural logarithm, where t represents the number of years since 2008, and f of t is the number of person trips in millions, approximates the curve reasonably well. And you can see the bar graph with the approximate numbers. So use this function to approximate the number of person trips in 2012 to the nearest million. And how does this approximation compare to the actual number of 1,588 million or 1.6 billion approximately? So T represents the number of years since 2008. So 2012 corresponds to T equals 4. We're going to evaluate this function of 4. We're going to evaluate f of 4. This is 1,458 plus 95.42 times the natural logarithm of 4. Okay, let's evaluate. On the calculator, this is 1,458 plus 95.42 times the natural logarithm of 4. And that's about, well, that's 1,590.28. And that was million. Okay, so the function approximates the actual number reasonably well. So the function approximates the actual number reasonably well. Okay, another application is example 6. And then I'm going to show you the change of base formula. So that's example 6 on page 452. That's another long problem. But yeah, we're seeing some applications now. That's 452. Geologists sometimes measure the age of rocks by using atomic clocks, by measuring the amounts of argon-40 and potassium-40 in a rock. It is possible to find the HT of the specimen in years with that formula here involving the natural logarithm, where A and K are the number of atoms of argon-40 and potassium-40 respectively in the specimen. So how old is a rock in which A is 0 and K is positive? Let's find out. So if A is 0, we have what? We have that T is 1.26 times 10 to the 9th times the natural logarithm of 1 plus 8.33. And then A is equal to 0, so that's going to be 0 over K. But 0 over K, if K is positive, that's going to be 0. So all this expression inside the parentheses. So this becomes 0. And what we have is something with logarithm of, with natural logarithm of 1. This is, so T, the time or the age of the rock, is 1.26 times 10 to the 9th times the natural logarithm of 1 over the natural logarithm of 2. But we know that the natural logarithm of 1 is also 0. That is, T is 1.26 times 10 to the 9th. This one is a 0. So that's going to be times 0 over whatever. But any number multiplied by 0 is going to be 0. So this means, so how old is a rock with these characteristics, with no atoms of argon 40? Well, this one is new. If T is 0, the rock is new. And in B, the ratio A over K for a sample of granite from New Hampshire is 0.212. How old is the sample? We know that A over K is 0.212. So we're going to evaluate A over K in that function. This is T, the age of the rock is 1.26 times 10 to the 9th times the natural logarithm of 1 plus 833 times 0.212 over the natural logarithm of 2. Okay, let's simplify whatever we can. So T is what? T is 1.26 times 10 to the 9th. And then times the natural logarithm. So we're going to simplify whatever is inside the natural logarithm. This is 1 plus 8.33 times 0.212. All that is equal to 2.76596. Over the natural logarithm of 2. And we're going to evaluate all that. So T, let's see what is T. We're going to approximate this to 2 decimals. Chances are that we're going to get an answer in scientific notation, but it's 1.26 times 10 to the 9th times the natural logarithm of 2.76596 divided by the natural logarithm of 2. Oh, so that's, well, that's an answer in scientific notation. That's approximately, okay, so before the decimal point, we have 9 digits. In scientific notation, this is approximately 1.85 times 10 to the 9. Or 1.85 billion years old. Okay, so we have seen a couple of applications. And the last part is the change of base theorem. That allows you to evaluate any logarithm with any base. Your calculator only has 2 buttons. Logarithm with base 10 and logarithm with base 8. So here's the question. So I know how to evaluate things like let's say logarithm of 4. I know how to evaluate that. Or natural logarithm of 0.31. It only takes 1 button. So on a calculator, I'm not going to share the screen. This is logarithm of 4. That's approximately 0.2 6, 0 to 0. That's approximately equal. A natural logarithm of 0. Or okay, we are picky about it. Let's make this one. A natural logarithm of 0.31. You can evaluate that with one button on the calculator. That's approximately negative 1.1712. Now the question is how to evaluate something with any base. Let's suppose we want to evaluate logarithm with base 2 of 3. If it was logarithm with base 2 of 1, that's 0. Logarithm with base 2 of 2 is 1. And logarithm with base 2 of 4, I can rewrite 4 as 2 squared, and that's 2. But logarithm with base 2 of 3, I don't have a button. So first I'm going to show you how to do this the long way. So let y be the logarithm with base 2 of 3. And then I'll give you a more direct formula. Then I know that 2 raised to the y power is equal to 3. So we're going to take natural logarithm on both sides. Okay, can be natural logarithm or can be decimal logarithm. For no particular reason, I'm choosing the natural logarithm. And properties of logarithms, they allow me to bring down the exponent. So y is natural logarithm of 3 over natural logarithm of 2. Okay, so we got something. But y was initially logarithm with base 2 of 3. So either logarithm with base 2 of 3 is natural logarithm of 3 over natural logarithm of 2. Now, for no particular reason, I chose the natural logarithm. But I could have chosen the decimal logarithm, and the answer is the same. So let's compare. You'll see that the answer is exactly the same. So natural logarithm of 3 over natural logarithm of 2 is about 1.585. And let's do with the decimal logarithm, logarithm of 3 over logarithm of 2 is the same answer, approximately 1.585. Now, you don't need to do this every single time. We have some formula called the change of base theorem. I'm going to copy that. And now you can evaluate any logarithm with any base on the calculator with either the decimal logarithm or the natural logarithm. For any positive real numbers, x, a, and b, where a does not equal 1 and b does not equal 1, the following holds. That logarithm with base a of x is logarithm with base b of x over logarithm with base b of a. In practice, we have either the decimal logarithm or the natural logarithm. So logarithm with base a of x is either the natural logarithm of x over the natural logarithm of a, or the common logarithm of x over the common logarithm of a. So those are going to be the last two examples. We're going to use the change of base theorem. to evaluate the following logarithms. Let's say you want to evaluate the logarithm with base 1.2 of 5.4. So I don't have a direct button on the calculator. Perform the change of base theorem. So for no particular reason, I'm using the natural logarithm. But if you want to use the common logarithm, that's fine. As long as you don't mix them, you're going to be fine. So let's evaluate natural logarithm of 5.4 over the natural logarithm of 1.2. That's approximate. Let's see what happened. I have a 0. Okay, so for some reason I got a different answer, but looks like this is correct. Yeah, I have natural logarithm of 5.4 over natural logarithm of 1.2. Let's try again. So that's okay. I didn't hit equal. So that's natural logarithm of 5.4 over natural logarithm of 1.2. Yeah, I didn't. Sorry, I didn't click on equal. So yeah, so that's approximately 9.25. Or if you prefer to use the common logarithm, you're going to get the same answer. Well, that's approximately equal. And finally, we're using the change of base theorem to evaluate the logarithm with base 1/3 of 20. This is by definition. I can use common logarithm or natural logarithm. That's going to be the natural logarithm of 20 over the natural logarithm of 1/3. Okay, so let's evaluate. So that's the natural logarithm of 20 over the natural logarithm of 1/3. Yeah, that's not working. So that's, again, that's the natural logarithm of 20 over, I need to use grouping symbols, natural logarithm of 1/3. Okay. And that's going to be about negative 2.73. Okay, and that's it. So with this, we finish section 4.4. Thank you for listening.